Hey everyone, and welcome back to the channel. Today, we're diving into a crucial question that often comes up after a tragic event like the recent Ahmedabad plane crash. What if the engine failure had happened at a different altitude? It's a somber thought, but, understanding the physics and pilot procedures involved is incredibly insightful for aviation enthusiasts and anyone curious about how aircraft operate under pressure. As you know, the recent Air India incident in Ahmedabad on June 12, 2025, tragically involved a Boeing 787-8 Dreamliner experiencing engine failure during a critical phase takeoff. Now, why is engine failure during takeoff so incredibly dangerous? Imagine this: limited altitude and speed. You've got minimal height and haven't built up much speed. That means very little energy, kinetic, or potential to play with. You can't just glide for miles. The V1 decision. Pilots train intensely for a concept called V1, or decision speed. If an engine fails before V1, they can often safely abort the takeoff. But if it happens after V1, as in the Ahmedabad incident, the aircraft is committed to flying. You have to get airborne, and then deal with the emergency. Ground proximity. Being so close to the ground gives the crew virtually no time to troubleshoot, attempt to restart, or even find a safe place to land. Any loss of control and impact is almost immediate. Asymmetric thrust. Losing one engine means uneven power, pulling the aircraft to one side. At low speeds, those crucial aerodynamic surfaces, like the rudder, are less effective, making control a real battle. It's a scenario pilots dread, where seconds feel like hours and options are incredibly limited. But what if this exact same engine failure had happened much, much higher? Let's imagine the Boeing 787's engine failed not during takeoff, but instead at its cruise altitude, say 35,000 feet. This is a completely different ballgame, offering several critical advantages. First, time. Glorious time. At cruise altitude, an aircraft has an immense amount of potential energy. Even with both engines out, a large airliner can actually glide for 150 to 200 nautical miles. That's minutes, even tens of minutes of precious time for the crew. With that time, pilots can calmly go through extensive emergency checklists. They can attempt engine restarts, manage fuel systems, and prepare the aircraft for an emergency landing. They can also communicate clearly with air traffic control, declare an emergency, and request vectors to the nearest suitable airport. They really have the luxury of choosing from multiple airfields. At higher speeds, the aircraft is more aerodynamically stable, making it easier to manage the asymmetric thrust from a single engine and maintain a controlled flight path. And high above the ground, the immediate threat of hitting obstacles or terrain is virtually eliminated. Now let's consider an in-between scenario: engine failure during the initial climb, perhaps between 1,000 and 5,000 feet. This situation is still very challenging, but offers slightly more wiggle room than a takeoff failure. You've got more time than during takeoff, but significantly less than at cruise. The pilots are still in a high workload phase of flight. They might have a few minutes to attempt an emergency return to the airport or identify a more suitable spot for a forced landing. Think of the Miracle on the Hudson, a perfect example of a controlled ditching in such a scenario. The aircraft is still relatively slow and low for complex maneuvers or long diversions. The priority remains maintaining control and setting up for an immediate landing. And the success here highly depends on the surrounding geography. Are there open fields, rivers, or clear highways? Or is it a dense urban jungle, or maybe even treacherous mountains? So, as you can see, in aviation, altitude truly is your friend. It translates directly into time, options, and energy, the critical assets that were tragically absent during the low-altitude engine failure in Ahmedabad. Every aviation incident is thoroughly investigated, and lessons are learned to make air travel even safer. While incredibly rare, understanding these what-if scenarios helps us appreciate the engineering, the pilot training, and the constant pursuit of safety that defines modern aviation. What do you think about these scenarios? Let us know in the comments below. If you found this insightful, please hit that like button, subscribe for more science and tech deep dives, and ring the notification bell so you don't miss our next video. Thanks for watching and fly safe.